All right, well, this video is going to talk about various things that we can do when analyzing graphs of functions, or whether or not something even is a function. So let's start off pretty quickly here with just a quick review of a couple of things. First of all, to tell if something is a function or not graphically, a great way to do that is the vertical line test. So determining, again, taking a vertical line, running it through our graph, and determining, again, vertical line x equals, right? Every vertical line has an equation of x equals a number. So such as x equals 1, you'll notice we cross our graph at one place. Well, does every point on our graph, again, if we look at a vertical line, does that vertical line only ever hit everywhere one time on our graph? We never get 2 points on that vertical line at the same time. Therefore, yes, this graph would be a function. The vertical line never hits more than 1 point. In addition to that, and if it is a function, then we could talk about function notation. Remember, function notation is talking about something like f of x, or g of x, or h of x. It gives us a way to refer to a lot of different functions at the same time. But graphically, we can actually use this as well. We're used to using it with equations much of the time, but on a graph, again, our function would be the red line on our graph over here. So we could determine what is f of -1. Well, I would go over to -1 on my x-axis, and I would go up to my red line, and it looks like, for the most part, we're probably going to be right at this point right here, which would mean that f of -1 was equal to 1 on our function. -1 being our x value, 1 being our y value, and we get that answer. We could also do that backwards. F of x, again, talking about the y value, f of x being 3, well, I would go up to my graph and I would draw a line up at 3 up here. And where do we cross at 3? Now that's going to be on this graph a little bit tricky to figure out, because taking a look at it, we're kind of just short of 2. So I might say something, if I had to estimate, maybe plus or minus, because notice we are in 2 different places over here, but they're pretty symmetrical, plus or minus maybe about 1.8. Again, all I can do off of a graph at best is estimate. We also could find certain points on our graph. Again, just a reminder, 4 different names for really the same thing. Zeros of a graph refer to, again, the x-intercepts. The one requirement x-intercepts, if we use those words, have is that they're real. Zeros technically on a graph would need to be real as well, but zeros of a function don't have to be. Zeros of a function could also be imaginary, if you remember. Roots is an older name for kind of all those same things, and solutions would be if we were setting our equation equal to 0 and solving, then we would also call them solutions to our equation. Whenever our function would come out equal to 0, when the y values are 0. Again, there's zeros, roots, solutions, and x-intercepts. Another thing we can find on our graph are what we call relative local minimums and maximums. Again, a relative local or relative or local maximum or minimum is just the high point on our graph or the low point on our graph over a shortened span. If all of the points f of b, right, are greater than all other f of x points, so all, or a point f of b, such as this one right here, that's greater than higher up, right, has a greater y value than all the points immediately around it. Sometimes it helps to think of this as kind of narrowing in. If we actually look at all the points right here, points are rising and rising and rising and rising and rising. But if we look at a narrower, a local part of our graph, the highest point in a short span would be considered a local maximum. And in that same way, the lowest point over a short span would be considered a local minimum. So what we can do is define those things. So we might be able to look at this and say, okay, well, this point right here, right, would be a local max, right? And we would be able to estimate that point. Looks to be, of course, it's labeled here, -2, -3 would be a local maximum. And then 0, 1 on the top part of our graph, again, we would call a local minimum. Local meaning, again, over a short span. Within a small area, it's the highest or lowest point on our graph. Notice we do need to write the entire coordinate. We're identifying a coordinate point, an ordered pair, not just what was the y value, or how high was it, or how low was it, minimum or maximum heights. It's the entire coordinate that's the local min or local max. Also, talking about our graph, we can also talk about the domain and range. The domain is all possible x values or input values. We often think of those as the input values, whereas all the y values or f of x values, those would be our output values. So thinking about our whole graph, we can use interval notation. We just learned about that. Interval notation to write this out. So from left to right, it looks to me, and I'm going to kind of assume that this graph continues onward here. Let's assume this is sort of a hyperbola kind of thing looking at here. And we've got an infinite graph, but we still are avoiding, notice we don't hit a vertical asymptote up the middle there, right at, looks to be about -1. Right? X equals -1 on there. So if I was looking at this and saying, okay, let's identify the domain, well, we're going to start at the infinite left over here. From the left, that's -infinity, which remember we can never touch, so it's not included, up to that -1, which again, we're also not going to touch. And then we're also going to include in union with, again, from -1 up to infinity on there. Then if we were talking about the range, if we were looking at the range of our graph, well, now we want to look top to bottom. Well, the range top to bottom looks like we're starting again at -infinity at the very bottom, but we're going to go up to that local maximum, so -3 in the y values. Because it is included, I'm going to put a bracket on there, hard bracket, in union with, and notice we have a gap. We skip a whole lot of graph here between -3 and 1. We're not going to touch any of that, but then we're going to start up again at 1, and we're going to travel all the way to infinity. Again, not including infinity because infinity is not real. So again, we can list off the interval notation, domain, and range of our graph. Again, what possible points exist? Domain from left to right as far as the x values are concerned, and range from bottom to top as far as the y values are concerned. Along that same lines, we can also talk about increasing, decreasing, or constant intervals. So looking at our graph over here at the right, it's kind of a funky one there. We could talk about when is our graph going from left to right upwards. So I would say that obviously from the bottom of our curve here, it's upwards, increasing there. But also at the left side, it might look like it's going down because of where the arrow goes. But again, from left to right, from left to right, our y values are increasing up to this cusp point here, this point, it looks like at about -1, -1 there. So again, this would also be part of our increasing interval. So for increasing, I would say we're starting at -infinity. We're traveling up to that -1 point. Now realize we're just talking about increasing and decreasing. So you always write them with open-ended intervals. At that top point, we are no longer increasing, or at that top point, we're not starting to decrease. It's just a point. So we can't include it in an increasing interval. But we do need to have both these parts. So it looks like that one starts at about 0. And again, would travel upwards till, let's just call this point, looks to be at about 2.5 maybe. And then up at, looks to be maybe, let's call it 4.5. A little bit above 4 there. So I'm going to stop my interval from 0 all the way up, again, just talking x values, to 2.5. Decreasing, well, again, that would start, yeah, let's do that in red. That's going to start at this point. It's going to go down to that bottom point and stop there. So we're going to travel from -1 to 0. And then constant has to be an interval over a horizontal line segment over here. So a constant interval, right, would be that top portion up here. So notice we're going to start at 2.5 and we're going to travel up to infinity on that one. It's going infinitely out to the right. starting at about 2.5, going infinitely to the right. Again, biggest thing, don't forget, they're open-ended intervals. At those stopping points, we are no longer traveling up or down. It's just a coordinate, so we got to stop there. We don't get to include. Notice no hard brackets in our interval notation there. Average rate of change is kind of an old one for us. Easier way to think of that is just the word slope. The average rate of change, again, the average change in the slope, essentially, or change from point to point as we go. Now, curves don't necessarily have slope, so that's the tricky part here. But if we take 2 points, we grab the 2 points that are on our graph over here, which look like we're missing a couple of parentheses here, but anyway. If we grab those 2 points, we can still find the slope between them. But again, it's not the slope along the red line. But if we took the average, if we drew a bunch of tangent lines, right, lines that would just touch our graph in one place, and we average them together, the slope of the line between our 2 points would actually be the average of all of those slopes. It's kind of an interesting fact. So the average rate of change, or as our formula says, the arc over here, the average rate of change just basically is the slope formula. Remember, the function f of b is just a y-coordinate. F of a is just a y-coordinate for points b and point a on the x values. So if we want to find the average rate of change for us, we're just going to say the y value 4 minus the other y value over, again, -2 minus 3. So we're going to get -5 over -5 equal to 1, and our average rate of change, essentially the slope between those 2 points, is a 1. Again, it's the slope of the secant line, the line that crossed in 2 places, right, through our parabola. But again, it's the average of all of the slopes of the tangent lines where they would only cross in one place, right, on the side of our parabola. If we drew a lot of those slopes, right here and here and here, and we average them all, that's what we would get. Finally, one last note, and again, we've talked about this before, even and odd functions. If we're looking at graphs and analyzing graphs, an even function, remember, is a function with y-axis symmetry. So it's a function that's going to be reflexive right across that y-axis. Any y value on our function would also have a negative x value. An x value on our function would have a negative x value with the exact same y value, right? We'd be able to reflect directly across our y-axis. An odd function, on the other hand, is going to look much more like a pinwheel, or a pinwheel around the origin, 180 degrees around the origin. Every point could be rotated around the origin and end up right back on top of itself, right? Your x-intercept here would rotate 180 degrees right on top of itself there. So it's going to look like it's rotated, and it has to be rotated directly around the origin. And then finally, looking at our bottom graph here, well, what about all the other graphs? What if it's not symmetric to y or symmetric to the origin? Well, then we just say it's neither. Most graphs we deal with actually won't have those symmetries. They won't be even or odd. That's why it's kind of very specific when we talk about those things. Kind of unique. All right, hopefully that reminds you of a whole lot of things about graphs. Good luck, and if you have any questions, make sure you talk to your teacher. Have a great day.